Okay, teacher, we can start.
Good evening, everybody. I welcome you all to this session. This is the day 5 of our workshop. Now, over to our beloved speaker, Professor Vishnu.
Good evening once again to all of you. So we are entering into the fifth day of the workshop, and till yesterday we have discussed almost all the basics in Python, like creating, using variables, assigning values, branching the program depending upon certain conditions, or using conditionals like if, else, else if, using loops, and importing functions. Defining our own functions was the last thing that we discussed yesterday. So we have seen how to define a function, how to access it, and only one thing that I didn't actually tell yesterday, that how to make use of the function, define it in another file. That means, suppose that we have defined a function in one particular file, how to use that particular function in another program. So it is exactly the same way in which we are importing libraries like math, etc. That means, suppose that we have defined the factorial function with the name my factorial. So for using my factorial function in another program, we need to just import that file by its file name. That is, we need to import whatever is the file name. I think yesterday we have used file names like 21 hyphen factorial, etc. So we need to just type import 21 hyphen factorial dot py and start using the function name as in the case of a usual function. That's it. But if you are using Colab interface, so if you are using the same worksheet, if you are not creating different worksheets for different days, so whatever you have defined on the top will be accessible to the code below also. The only thing is that you need to run the entire notebook once. Whenever you are starting the notebook, every day you need to run the entire code from top to bottom once. Then only the above written things, even though it's visible, it will be accessible for the below cells. Okay, that's your way. So today we are going to see something like some basic libraries available in, not basic actually, it is somewhat advanced libraries in Python, like symbolic Python or sympy. And after that we'll try to see the other libraries like sympy, matplotlib, numerical Python, etc. Numerical Python already told. Okay, sympy is there, scientific Python is there. So we will try to see using these library functions and some mathematics problems using these library functions or libraries. So we are going to start a new program using symbolic Python. That's the very first thing that we are going to do today. Let me start sharing my screen. You can see the spider interface which I'm using now. Let me start a new Google document also for pasting the code which I'm typing. So this is where the Google code that the Python code will be pasted. Okay. So as I told, we are going to start a program in which we are going to make use of the symbolic Python module available in Python, and we will try to see what are the features, what are the options, what are the different things that's available in symbolic Python, which are not actually available in the C math library or math library. Symbolic Python, as you can guess from the name, that uh, we have been using variable names, right? We have been using variable names for using the values inside that. Okay, I'll start typing, and with that, I shall try to explain. So today it's the 26th program. We are starting. This is 26. So SymPy Basics is the program name. Okay. So whenever we want to use a symbol, for example, x. So in mathematics, we know that x plus x. In mathematics, we know that x plus x is nothing but 2x, right? But if we try the same thing in Python, what will happen? So name x is not defined. That's the error message that will appear. Okay. Now, suppose that we are giving the value x is equal to 1 or 1.5, and then x plus x is permitted to be equal to 3. So the value is correct. Now, on the other hand, you may write y is equal to, now, um, y equal to from math import sine pi, y is equal to sine pi by 4, print y square. So the value will be shown here because y square, the value is root 3 by 2, so 3 by 4. So 3 by 4 is going to be 3 by 4. No, that's not correct. Pi by 4 is how much? 1 by root 2, sorry. 1 by root 2, the square is going to be equal to 1 by 2, which is approximately 499, etc. So everything is shown. But here the problem is that we need to assign some value into y, assign some value into x for making use of that in our program. Okay, we cannot directly use. This is not correct. If we use something like print z plus z, that's not going to make any sense because the name z is not defined. So we are going to try to avoid these difficulties by we are going to define x to be a symbol instead of giving any value to x. We will simply say that x is going to be a symbol and x plus x is going to be so that x plus x we will get the answer to be 2x, x into x we will get the answer to be equal to x square, and so on. Okay, this is the attempt that we are going to make now. So for that, we need to import one library function from sympy. Remember, the name is sympy, using module sympy. So from sympy, so if you want to see what are the okay, we will try to see what are the available functions in sympy later. So from sympy, import symbol. That's a function. Okay. Afterwards, let us try to define. Remember that x we have defined previously to be equal to 1.5, but instead of that, we are going to define x to be a symbol, not x to be the symbol x. Now, what is the effect of this? So let us try to see what x is. It took some time for importing. After that, it says that it belongs to sympy core symbol. Okay, this is a symbol. Now, let me suppress that. Print x plus x. What is the value of x plus x? As we expect, it's 2x. Okay, now let me define y to be equal to symbol y. So, what is the value of x plus y, or x plus y plus y plus y? What's the value of this? 2x plus 3y. Okay, so we have simply defined x and y to be symbols. Remember that the left side we are typing, we are writing x, and the right side we are writing x. This actually doesn't matter. Even if you are defining, even instead of x, if you are typing here x, then you need to use, that's it. It doesn't matter that you are defining, you are putting the symbol x into which variable. Doesn't actually matter. It's perfectly correct. No problem. Okay. So, but that is not going to make much sense. So we usually define it like this. Okay, let me update the Google document with this. Done. Of course, you can mix up numbers and symbols. Print x plus 2 plus x. So 2x plus 2. That makes sense. Also, x minus x, y by y. X minus x is given to be 0, and y by y is, the answer is given to be equal to 1. Now, of course, that you can keep the symbol x inside any other variable also. Like for example, suppose that a equal to, or x equal to x, and suppose that we use capital X later, and what do this capital X hold? We can ask like this. This is not necessary, I think. So, what do this X hold? X holds small x. So the name command, name method, not exactly a method, because it is not doing anything on this x, but simply displays the value of that. But if you want to define multiple symbols simultaneously, that's also possible. For example, suppose that we define A, B, C equal to, but for that we need, instead of a symbol, we need symbols. But that symbols is everything in small letter. A, B, C equal to symbols. You may either write, I think, X, sorry, A, B, C, then it's missing, and print ABC, Symbols take, okay, so this is not correct. Instead of that, you need to define just a comma b comma c inside this. Let's see this. Okay, that's correct. So enclose everything inside one single double quote. Is it going to work? I don't know exactly. Let us try to say that. So double quote also works. So enclose everything within one single pair of quotes separated by comma. Multiple symbols can be defined like this. So any mathematical operations can be carried out on these symbols. A square or minus 2a square. Oh, sorry, 2a square you cannot write like this. 2a square, that's minus a square. Now, a plus 1 into a minus 1. So a minus, it is just shown as a minus 1 into a plus 1 instead of multiplying. But if you want to multiply, you need to use another function, expand. Now, expand a square minus 1. The same way we can factorize also. But you need to again import. Import factor a square minus 1. So a square minus 1, you're expanding, you're factorizing. Updating the Google document and that. Okay, these are some basics of symbolic Python. Now, let us do something more. Let us see how far this factorization will, how far this factorization is going to work. I don't exactly know. Let's try to do that. Print factor. Will x square plus 1 be factored? I don't exactly know. Square, x square minus 1 will be definitely. Okay, otherwise, x square minus 2 will it be factored? No, it's factorizing only in terms of integers. and therefore naturally you may not be able to factor not factorizing. Okay, let us try one more. Factorizing x square plus 1. X square plus 1 is also not factorized. So, what is the guess probably you want to make from this? That this factorization a square minus 1 is being carried out, but x square minus 2, x square plus 1, these two factorizations are not working. Okay, so in fact, if you want to factorize, I will try to explain the second one first. So, if you want to factorize, this is not going to work. The problem here is that sympy is actually looking for a root of this x square plus 1, root of this polynomial over the set of all over the set of all rationals. Okay, we need to clarify even that first. Is it over the set of all rationals? Let us see x square um, minus x square minus 1 by 4. Let us try factorizing this. Okay, even this is working. X square minus 1 by 4. Even this is working. Okay, let us try one more. X square minus 1. What should I try? So suppose that x minus I into x plus I am multiplying. Oh, okay, that's not the thing that I want. So maybe I can try with x square plus 1j. 1j stands for the imaginary number. What is the result of this? The last one. Here you can see that even though we have written 1j here, Python, the symbolic Python factor function is converting that into I. See, this is actually a kind of problem with any open source software that many people will be contributing and they will be using their own notations. So there can be some inconsistencies here and there. So basically, because of that only, it seems that there is an inconsistency in the factorization of this particular the last line is giving some strange factorization in terms of I, not in terms of j, but in terms of I. Most probably that's correct. Most probably that's correct. Let us try to see it in expand. This j is not valid. Still j is not valid. Why? What is the result of this line? Okay, before that, let me just try to delete it. I think one. Okay, this is a full line. I think this is a full line. This is a factorization. This is the factorization, and okay, this is the factorization. This is what x square. Oh, it is not giving any factorization. It is exactly showing the same thing back to us. Oh, right, right, right. I didn't actually understand that. I didn't notice that. This is nothing but 1 into 1x square plus I. That's it. There is no factorization taking place even here. Okay, let us see that what are the remedies that we can find for fixing this problem. That the factorization is not happening entirely, because when we are trying to factorize x square minus 2, we want the factors to be x minus root 2 and x plus root 2. That is not exactly happening here. Okay, and when we want to factorize x square plus 1, we want the result to be x minus I into x plus I. X minus I into x plus I. Okay, let us try to see that first. X minus I into x plus I first. X square plus j. So in the factor function, we need to give an extra argument. So we need to use the complex extension. I think we need to import I also from 10I is not a valid algebraic number in QQI. So what's happening here? X square. Oh, sorry. This is not. This is the correct thing. Okay. So you just try to understand what exactly you have done here. So here, okay, maybe I can give even J here. Will it work? No. The I is the only possibility. So we need to import the sympy simple capital I first of all. Secondly, we are going to tell that the solution, the factorization of x square plus 1 is required in the field, not exactly in the field, in the, okay, in the field only, Qi, the set of all elements of the form um, R, R1 plus R2I, where R1 and R2 are rationals. I is the imaginary number. That's a field, right? Is that a field? Is that a field? So what is it exactly? R1 plus R2I. So that is a field of with degree of extension 2 over the set of all rational numbers, right? I guess so. So we are trying to find the solution, and in fact, for finding the solution over some field is not necessary. The solution can be, in fact, over some ring. Okay, the solution can be actually some over ring. Here we are trying to find the solution over Qi. Q, no, no, the exact symbol we are trying to use is, okay, finding solution over Qi. That's what's happening here. So an equivalent command is not exactly equivalent. Okay, suppose that we have Gaussian integers. Okay, now, but there is actually certain difficulty that to find out a solution, you need to clearly understand. If you are using this method, you need to clearly understand that in which field the solution is going to exist. But we know that over the complex field, all kinds of solutions do exist. So we can use the complex field itself if required. So the domain of the solution, we can declare it to be the complex field. That's possible. Okay, something like this. Factor x square plus 1 or x square plus 2, and let us use the domain to be equal to x square minus 2. I will use first. Domain equal to r. Try to see this. So x square minus 2, the solution turns out to be, we would have expected, what is the solution that we expect? X minus root 2 into x plus root. But instead of that, it's shown in a different way. It's shown like 2 into x square by 2 minus 1. X square minus 2 by 1. So which is equivalent to x square. Uh, no, this is still not factorized. No factorization is still happening here. X square minus 2. Even here, the result is x square minus 2. The result would have been, even here, that's not working. So what should we require? Okay, let me just try one more method. Even this is not working. This method is also not seeming to go, not seems to give, does not seem to give the correct result. Let me try one more. So let us extend this by roots of this polynomial. So let us take this to be this is a polynomial. So trying to factorize it over an extension which contains the roots. Extension equal to extension equal to roots of it. Roots of polynomial, not the polynomial. Roots is not defined. Okay, let us import even that. Okay, this is the only thing finally working. X minus square root of 2, x plus square root of 2. Okay, let us try to make use of this problem. Factoring over. So x square plus 1, let's try. Oh, we haven't changed the polynomial here. We can simply write polynomial x square plus 1, factoring over root extension x minus I into x plus I. Yeah, this is working perfectly. So to find out a root of any polynomial without explicitly mentioning over which field, over which ring we want a solution, we can use the roots function. Use the roots function and extend and inform sympy that we want the solution to be in an extension of the rational numbers where the roots of this polynomial is present. Let me update the entire thing. Updated the entire Google document with this new set of comments. Please try this and try to find out some extra solutions. Maybe can you try to find out solutions for x square plus root 2 in Google Colab? X square plus 2. Sorry, not root 2. X square plus 2. What's the solution? There is another way of printing the roots properly. That is known as pretty printing function available in SymPy. Pretty printing. So pretty printing, we need to import first so that we can see the output in a little bit neat way. I don't know whether it will work in the Spider interface or in Colab interface. That usually works in interactive Python. I think it works, and in ideally it doesn't work. In Python, ideally, if you are using it, doesn't seem to work. But Colab it should work, and interactive Python also it should work. So from and let's try to see this. Not printing, but pretty printing. Ah, looks a little bit nice. X minus I and x plus I looks slightly better. And if you use this, okay, instead of saying this is the, we can straight away put it here and use productivity. Maybe we can remove this and try. Yeah, output is bit neat. X minus root 2 into x plus root 2. And the pretty print can be used for more things like expand x plus 1, x minus 2. See that this the square is appearing slightly above. Okay, to just to make what do you call the impression that this is x square, even though it doesn't really look that nice. Okay, it's somewhat it's comparatively better. So pretty print p print x square minus x minus 2. But on the other hand, if you want minus 2 minus x minus, if you want the polynomial terms in the increasing ascending order of the powers, that means the order reversed for this x square minus x minus 2, you can even do that. You can reverse the order. So you need to use the init printing command, init printing function. Now reverse the order of pretty print, reverse lexicography, means dictionary order. Try with this once again. Sorry, it didn't work. We print expand x plus 1 into x minus 2. It's appearing as x square minus x minus 2. Right? It's like that. The order is reversed. In printing. But this is exactly the same. Okay, I think we need to change this. This is not really necessary, it seems. Maybe instead of that, here itself this can be put. Okay, so there is a change in the sympy version. Therefore, the init printing, the use of that init printing also has changed. You can mention inside pprint itself that order is in the reverse lexicographic order. Okay, so not as a separate init print, a init printing command, but inside print itself. X square minus 2. How far I have updated? Okay, updated the remaining thing also in Google document. You please try. Okay, now we should also know that once given a polynomial, how to evaluate it. Okay, once given a function, once given a polynomial, how to evaluate this thing. For example, okay, sine function already we can evaluate. There is no problem. But if you are defining an expression, and if you want to evaluate that particular expression at some particular point, we need to put some value into that. Okay, let's try to see that. So the next thing that we are trying to see is evaluating expressions. So suppose that we have the polynomial equal to x square plus 2x, or 2x is not going to work, plus 3, for example. So let us evaluate it. Suppose that we evaluate it at c equal to 2. What we need to essentially do is, and the value is formatting. So the polynomial is here, c is here. Now the evaluation, for the evaluation, we need to simply substitute. So whatever value we want to, uh, whatever expression is there with us, we need to use the substitute method. And inside the substitute, we need to, by defining a dictionary of variables, we need to assign the values in the following way. So polynomial substitute. So what to substitute? The value of x to be substituted as c. That's evaluating x square plus 2x plus 3 at 2. So at 2, the value is 4 plus 4 plus 3. That's 11. Fine. Okay, this is how. And suppose that on the other hand, suppose that we have more than one variable to substitute. For example, suppose that we want to evaluate the expression circle, or not circle exactly, circle expression, if you want to say x square plus y square. Suppose that you want to evaluate this. Let's make it simpler. Evaluating this circle, or the expression CARC at or whatever value c is equal to, say. So for that, you need to substitute. The only thing is that x, okay, you want to give x naught equal to 2, y naught equal to 1. So circle at x naught, y naught, substitute x value x naught and y value y naught. So x square plus y square at 2 1. So 2 square plus 1 square, which is 5, which is 5. So it can be evaluated. See that the structure that we are going to use is actually a dictionary structure. Okay, we define a dictionary in the following way. Using inside curly braces, we used some labels, label colon value. So the value of x is to be substituted as x naught. So x colon x naught. Y is to be substituted as y colon y naught. This is the way we are using this substitute command or substitute function. Pardon. Whatever we want, we can substitute. There's no problem. We can even substitute a itself here. A b. So it becomes a and b are symbols. A and B are defined to be symbols. A square plus B square. That's it. We can even substitute A plus B. That's also possible. Or no need to put a bracket. A plus B. That's it. So A square plus A plus. Maybe we can even simplify this further. From sympy import simplify. I don't know what the simplify will be. Okay, A square and A square should go together. That's what we expect. Giving 2A square. That's not happening. So let us try to expand and see. 2A square plus 2AB. Okay, there is no further simplification happening here, but okay, if you expand, I don't know, simplification and expansion, what exactly? Uh, okay, I don't really see an example where simplify can actually be used. So I'm not using that. Maybe I can try to explain it later. I don't see an example where simplify can be actually employed because what I'm exactly trying to do here is being it can be achieved easily by using the expand function, not simplify function. Simplify function that means that say some radicals should be cleared off, etc. So from okay, let me not try to do that. Okay, instead of that, let me try to just this can be actually the symbolic Python can be used for writing down series expressions symbolically. For example, we know that the series expansion of e raised to x. We know that is nothing but it's 1 plus x by 1 factorial plus x square by 2 factorial plus etc. Let us try to expand it using the symbolic Python. and let us try to write down a few terms of that and try to see what exactly the value is. And let us try to see the error in the approximation also. Okay, because this e raised to x is equal to that's a kind of expansion. So that expansion, if we are dropping the terms appearing in the tail of that, definitely there is an error. Let us try to see that how much the error is. Let me update this before going to update the Google Sheet before going to the next program. Okay, I'm starting a new program. So this is for finding series expansions. So let us try to find out. We know that the value e, the constant e is present in the math library. Let us try to make use of that. And after that, we want to expand e using the expression that 1 plus x square plus etc. And afterwards, we will try to see the difference between these two. The direct value of e and the time by time expansion and what are the approximations, how much the error is. And the error is if the error is converging to zero or not. Of course, we cannot check the convergence at all distance using sympy because for checking the convergence, we need to take infinitely many times. That's a theoretical thing. We cannot do it using computer, but we can just see at least that what exactly is happening. Okay. So what is the first thing? So we will import e from math first, or otherwise we can import e from symbolic Python itself. Let me see if symbolic Python is there. Sorry, if e is there in symbolic Python, sympy, import sympy. Now print dir sympy to see the contents inside. So what are the contents inside that? So these are all available in symbolic Python. Too many things are there. I'm just looking at E. If E is there, I don't have to import it from. No, the E value seems to be missing from that. So let me import from math, import E. Okay. So my aim is to find a series expansion for e raised to x, to show a series expansion for e raised to x. Not only that, I would like to compute the value of e raised to x at certain specific x's and try to find out the error in the actual computation of e raised to x and the computation of e raised to x using the series expansion. Okay, that's what I want. And we are assuming that we know that the series expansion for e raised to x is 1 plus x by 1 factorial plus x square by 2 factorial plus etc. Okay, that also we assume. So from sympy, we need symbol x. Okay, symbols can be used for even printing just one symbol. So now E is here, X is here. Both are. So first of all, we will try to write down the find out the series expansion. So how do we find out the series expansion? So series expansion can be found out by expansion. So we are starting with one because we need to keep on adding it to it. Suppose that we want the first 20 times. So we do it in a loop for I in range 1 to 21. Already the first time is there, so let us start with 2 to 21. We need the factorial function also. So what do we need? We need to add 1 plus x square plus x square. So to expansion or ex for e raised to x or e to x, e to the power x. So what do we need to add? We need to add x to the power. So how do we find the power? Maybe we require the power function also. Pow. I think Pow is not a part of math, but it's already available there in direct Python. So let us see that again. X2 power of x to I and divided by factorial I. So let us see it the first, say 5 times. Let us try to see. Okay, this power is not working. So from where we can use power? Is there any power in symbolic Python itself? Power. This is not necessary. Sorry. Since we are using integer power, we can directly type x double star. No need to use any of these things. So let us drop the power function. Okay, the expansion is this. Maybe the PP print can be much more useful. So this is 1 plus x square. This is in the reverse order. Maybe we can reverse the order. 1 plus x square by 2. Oh, what is happening to x by 1 factorial? So we need 1 here. Sorry. X by 1 factorial is just x. That's evaluated, simplified. X square by 2 factorial, x cube by 3, x raised to 4 by 4. It's working fine. Seems to be. Let us take 21. It's too large. 10. It's better. This is the expansion. Let me update the Google document with this. Done. Please try. This is actually the Maclaurin series because we are expanding it around zero. This is the Maclaurin series. So this expansion is around zero. So this expansion is around the number zero. So if we expand it around the number a, arbitrary number a, that's known as Taylor series. So let us see the value difference. How do they differ? So let us try to see the difference in values from 0 to 10. Remember that this expansion is actually valued at 0. We will try to just see that what exactly is the difference between the actual value and the approximate value when we evaluate this expression from 0 to 10. Print the actual value and series value at C. The actual value should be e to the power c, and the series value should be what is it? We need to evaluate, substitute for x the value c. Why is it showing us a numerical approximation? Let's try. Okay, so here we are seeing that the error. Okay, let us try to see the error first of all. Instead of looking at this, let us try to find out the error. Error means the actual value minus approximate value or the absolute value of that. Absolute value of minus this. You can see that the error at 10 is 11939. Too much. Let's try to put more terms into this. 11939. Let's come down to 34. So highly negligible at 10. So what is your impression about this expression then? So what do you think of this expression? Okay, let me update this first. See that instead of trying to understand just programming, I think it's better if we try to understand some mathematics also along with that. Instead of just trying to understand how to code, programming should be actually used for making inferences, not for finding the exact answers. You cannot most of the times, but you will be able to make some guesses. You will be able to find out certain things. So, what do you think about the expression? What do you think about this expansion? When the number of times increases, the expansion is giving better approximations, even at numbers at large distance from zero. Okay, when number of times is less, the approximation is giving more error. But see that the error is increasing with the distance. If you are moving away from 10, if you are moving away from 0, the error is increasing. Because the Maclaurin series expansion is the Taylor series expansion around x equal to 0. Okay, the Taylor series expansion around x equal to 0. Now, on the other hand, suppose that we find the Taylor series expansion itself, suppose at x equal to 10, and do the same exercise for 0 to 10. Let me save this file as. Remember that these are the values. Okay, if I am using um, 11 times, expansion up to 11 times at 10, therefore I am getting at 10 I am getting at 10 what I am getting is the value is from okay the error at 10 is 9184. Just remember that in your mind. So suppose that I move the expansion from the center of expansion from 0 to say 5. See that the error now is just note down the error now is what happened there? Where is it? 9184. Suppose that now I move the center from 0 to 5. Okay. Let me just save it as instead of modifying the file. So this becomes sympy Taylor expansion. So for Taylor expansion, remember that what are the things that we require? So the definition of Taylor expansion is that you need. Oh, I also forgot about that. How is a Taylor expansion defined exactly? Taylor series is Fn a by n factorial x minus a to the power n. Fn a is nothing but this is 0 raised to x. So uh, If you expand e raised to x, Taylor series expansion that we want is Taylor series expansion of e to x at 5. This is what we want. So, how do we find the expansion? So, the expansion is going to be just 1 second. Find out a form for that. So we have f of x equal to f of a, and here our a is nothing but 5, right? We are trying to expand it at 5. So, oh, no, f of 5. F of 5 is nothing but e to the power 5. So e to 5. We are trying to expand it in terms of e to the power 5. After that, what should we add? F dash a. F dash a is nothing but f is e to the power x. Therefore, f dash x is also going to be e to the power x. Therefore, we again need e to the power e of 5 only essentially we need. Okay. So how can we write the formula completely? So f of a, which is e to the power which is e to the power 5, f dash a, which is again going to be e to the power 5. So essentially, it's going to be e to the power 5 into 1 plus x minus a by 1 factorial plus x minus a the whole square by 2 factorial plus etc. Am I correct? I think it's better if someone corrects me, because otherwise I will be writing some program and all of you will be understanding it like that. The expansion that I'm going to use is, because the Taylor expansion we know that it's equal to it's f of x is equal to f of a plus f dash a into x. Okay, I will write that. That's better. So Taylor expansion is f of x equal to at a f of a plus f dash a x minus a by 1 factorial plus f double dash a x minus a square by 2 factorial plus etc. In this formula, just say that f of x is here e raised to x for us. So f dash x is again e raised to x. So f of a, f dash a, f double dash a, etc. Everything are going to be just e raised to. So what do we get finally in that case? I am a little bit confused about this. So the expansion is this expansion is correct. What I'm wondering is to find out the Taylor expansion, what are the things that we need to actually do? Okay, let me just try to put f of a itself here instead. That's 0, a is equal to 0. This is 0 raised to 5 essentially. Okay. Okay, so let me just try to multiply this with e raised to 5. So e raised to 5 is appearing here, and e raised to 5 is appearing everywhere. In fact, therefore, I can just take this 1 to be the initial term, multiply with f of a, f dash a, f double dash a, everything is going to be just equal to e raised to a. So let us multiply e raised to a towards the end. Okay, there is no need of keeping that here itself. We can multiply with e raised to a towards the end. So after that, okay, x minus what is this a? A is not defined here. A we were thinking that we will put something. Okay, for the time being, let us define a also to be a symbol. After that, we can put the substitution. A symbol a. So x minus a makes sense. X minus a to this power by factorial. So towards the end of that, let us multiply. Let's multiply e to x with with what? With e to the power. Oh, but e to the power a is not going to make much sense. That's it. E to the power a is not going to make much sense. I don't think that e to the power a is okay. Let us try to see that e to the power a is just a symbol and it's going to be treated as just a number. Therefore, e to the power a makes some sense. Okay, let me try. So e to the power x. Now e to the power x is now printed. So now this part I am just commenting out. That I'm trying.
Sir, a to x star equals
Sorry.
not plus equal. E to x,
Here.
is it star equal?
Here, right? It's correct now?
Yes, sir.
Okay. Thank you. So how many times I have evaluated? Maybe let us try with some 4 times in the beginning, just to see that. So something to its power a, 1 plus x minus a the whole square. What happened to x? What happened to x minus a to the power 1? By 1 factorial. What happened to that term? Is that term
Is that
missing?
the fourth term?
Sorry. That has gone to the end. I was checking for it in the beginning. Sorry. One. So one is appearing in the beginning, and then square 3 somehow x minus 3 is appearing towards the end. Okay. Order. Let us just don't try to do anything with the order. Okay. Even this is not really that neat. Okay. Anyway, I think the previous one was better. So 1 minus x minus a. Okay. Let us try to evaluate this and see if the evaluation is star 4 times. Now trying to evaluate this. So we need to evaluate. So this is a generic evaluation. So we need, say, e to 5. That's what we are trying to evaluate. E to 5 is nothing but instead of a, we need to substitute. E to 5 is nothing but instead of a, let us substitute. What is the substitution that we require? Instead of a, put 5. Okay, this is the substitution that we require. Let us try to print this also. Hopefully this is correct. Now let us try to evaluate this. Now e to 5 we will evaluate it during in the range. The last thing. So the error at 5 is 5.6843 etc. into e to the power minus 4, which is negligible. So the error here is 5.6 something. And the error here, sorry, not this one. At 5, the error here was 2 point something. At 5, the error here is e to the power minus 14, which is scientific notation, which is 10 to the power minus 14. Okay. The error is negligible when we are trying to evaluate e to the power 5 with a equal to 5. So, which essentially means that the Taylor expansion, if you are using the Taylor expansion, if you are trying to find out the value of a function at one particular c, that that particular approximation is going to be valid around some a. So if your c is very close to a, the approximation is going to be much more correct. If your c is far away from your a, the approximation is going to fail. Okay, that's actually the the final moral, maybe I should say. So if you are using Taylor series expansion, make sure that Taylor series expansion is not. Once you find an expansion, you cannot use it everywhere. Once you find the expansion, you cannot use it everywhere. So for evaluating everything, you cannot use that. Okay. So once your Taylor series expansion is defined at A, you can use it for approximating the function around A, not everywhere. So similarly, if your Maclaurin series expansion is defined at 0, so use it for finding values around 0, not for not at distances far away from that. Okay. So this is how we can have a look at the series expansion. Not only that, we can evaluate, we can try to approximate, we can try to find out the error in the approximation, we can try to see, we can try to understand the basic concepts in mathematics using computer, mathematics using program. So remember that programming cannot be entirely used for proving anything, for verifying anything completely, but programming usually gives you an idea. Programming usually gives you an idea about uh, um, what you are trying to see can be now seen with some concrete examples. But suppose that you are trying to do all these things on your own using your book, paper, and pen. So this will be a tedious job, difficult job. Most of the times, you will be simply assuming, you will be simply thinking that okay, this is going to be correct. And to be frank, I have never tried to see the Taylor series expansion of any number. when I was learning the sales expansion. I was just assuming, I was just taking this for granted. I was just ready to accept that result to be true without even checking if it's going to be true for some number, if it's going to be true for if the expansion is going to be accurate at a certain distance. None of these things I have verified. And I think most of the students and teachers as of today might be on the same side of uh, the book or the page as I do. Many of the teachers and researchers, students might not have checked whether this expansion is valid at some point at a distance of at a reasonable distance from the city. That's what I think. Okay. I hope that you could understand this program properly. You could understand what exactly the motive was, what exactly was the motive behind doing all this kind of expansion, writing code, seeing the approximate value. Now, if you want, you can try to see the approximation at some other point also. Here, see that the error at 10 is 1, 2, 3, 2, 3. Suppose that instead of this, we use 10 and find the expansion around 10. 1, 2, 3, 2, 3 is the error, which is very huge. 5, 15. At 10, the error is negligible. 11 onwards, the error is starting to go up. So only in the very close neighborhood of this number, it's going to be true. Maybe you can try 10.1, 10.1. See that at 10.1, the error is still negligible. And of course, if you increase the number of times in that expansion, the error is also going to become smaller and smaller. Either you have to increase the number of times or you need to take the A to be very close to the number where you are trying to approximate. Otherwise, the expansion is not going to make much sense. Your expansion and the value that you are going to get will not make much sense, will not be useful, okay, for any practical purpose. Okay, that's all about series expansion, and we can find out the series expansion of many such functions. You cannot find out series expansion. You can find out series expansion provided that yeah, you can feed the derivatives here. Here you have since the derivative of e raised to x was e raised to x itself, the job was much easier here. But in the case of some other functions, the derivative is not going to be exactly like this, and in such a situation, uh, we need to ask Python to find the derivative also in addition, right? So just by directly typing the derivative is not going to make much sense when we have a different derivative. So in such a situation, we need to use something else. Okay. So what next? So we have tried with expressions. Let us try to see something else is left for actually. Okay, solving. So we already had done something on factorization, series summation. We have discussed those things were actually supposed to be for the next 2 3 days, but I have somehow for keeping the logical flow somewhat slightly better, I just changed the order slightly and introduced factorization and summing of a series today. Okay, so in addition to that, solving equations and plotting needs to be taken up tomorrow. Okay, solving equations and plotting using symbolic Python needs to be taken tomorrow. Let me try to see if there is something else that is left here for today. So we have already seen, we have not seen solving equations, but instead of that, we tried to factorize it. That yes. Okay, let me give the feedback link to the YouTube page also. 1 second. I'm just checking if there is anything extra from this topic itself I can discuss today, uh, instead of going into tomorrow's topics directly. Yeah, one more thing I would like to tell that using this particular symbols function that we have imported from sympy, we can define variables like x1, x2, x3, x4, etc. very easily. So most of the times, what happens is that we need to define x1, x2, x3, x4, etc. explicitly, like defining. Okay, let us see one program defining more variables. 29. So from SymPy, okay, have I updated the entire thing, previous thing? I think so. Let me otherwise do that once before going to the new program. Oh, this was in fact 28. Okay, I have updated the Google Sheet up to the previous one. Okay, now what I was saying is that for defining multiple variables with the same name, like in mathematics, most of the times we want to define variables like x1, x2, x3, x4, etc., or x11, x12, x13, etc. So for defining variables or symbols, so for defining variables or symbols like that, there is actually a quick way to do things. Okay, from SymPy import, or from SymPy import symbols. Symbols was with small letter. Uh, this you need to be really careful because these two are using for some unknown reason. This is in capital, starting with capital S. Here it is small. Okay, we don't really want this. We want symbols. So for defining x1, x2 variables, x1, x2, etc., we can define it either like this: x1, x2, x3 equal to symbols x1, x2, x3. This is one way. So we haven't used it. Now, an alternate way is probably that instead of doing like this, okay, let me try. Okay, let me try that. I'm not exactly sure about the way in which this function is working, the way in which the this list is going to work. So I want to define a1, a2, a3. Okay, so a1, a2, a3. So for that, I'm going to use the following command: symbols. So symbols a 1 to 3. I don't know whether it will work. I'm just trying to see. Okay, let me just try to see what the value is. Oh, great, it's working at least. A 1 to 5. So what's happening here is that here we are defining a triple consisting of A1, A2, A3. So five symbols we have defined in one stretch. Okay, of course we can convert it into a list if you like. So we have defined a list of symbols here. Okay, A1, A2, A5. So if you ask for type of A1, sorry. I think we need to use it like this. In that case, uh, okay, A0 itself. A0 is a symbol which is A1. If I ask to print for A0, I'll be having A1 here, and another way is uh, a two-dimensional symbols list also I can define the same way. So for that, so suppose that I want A11, A12, A13, A21, A22, A23, etc. like that, and A51, A51, A52, A53. Then in such a situation, I need to use this one, or let me put B. B. If I use 1 to 4, okay, what am I going to get? So I will get B11. So here the variation is that B1 to B5 is created. Okay. B1 to B5 is, sorry, B1 to B4 is created. But in B1 to B4, again B11 is created, B12 is created, B13 is created. That's it. So altogether how many? 12 of them, because here we have 4 of them, because 5 minus 1 is 4. Here we have 3 of them, 4 minus 1. So 4 and 2. So this is one way to define a number of symbols simultaneously. We can define multiple number of symbols simultaneously using this. And one more is that using sympy you can represent rational exactly like that. Instead of converting rationals into the decimal equivalents, like if you use print 1 by 3, then you will be getting 0.33, 1 by 3 star 3. You're getting 1 point. Okay, that is correct. There is no problem. 1 by 9. So, but basically, this is what we call an approximation, because we are actually multiplying. Okay, let me just save this 1 by 3 to decimal expansion. 1 by 3. This is 1 by 3. Now 1 by 3 into DEC. So still giving the correct answer. There is no problem. But now, okay, one more thing is instead of this, math from math import sqrt of 2 and print this. What is the result? And what is the square of this? Square of this is approximated here. But instead of that, I think you can import sqrt from directly from the sympy itself. So that you can retain sqrt exactly like that. Let us try to see if sqrt is there. From sympy, import sqrt. Okay, let me just try to, yeah. So if you are using sqrt from sympy, the effect is that, okay, if you want to, so I will do it in two ways. From sympy, import sqrt, the result of that I will show. So the advantage of using sympy, that's what I want to stress. So suppose that we are importing sqrt from math. Suppose that we are building it. So the result is where is the result? Yeah, the result first is 2.00 etc 4. The result in the second case it's equal to 2. Okay, so here the sqrt of 2 is preserved as square root of 2. It's not converted into decimal expansion. That's why it's appearing like that. So can be seen because of this print. So what is this? SQRT of SQRT2 is not converted into decimal form. It's just preserved as SQRT. That's it. Okay, this is an advantage of using this what you call a sympy function. And one more example probably. So square root of 2 into, or otherwise square root of 8 into square root of 2. Remember that this is from sympy. It turns out to be 4. But if you are using exactly the same command here, our result is going to be 4.00 etc. 1. Okay, this is because square root of 8 is just preserved as square root of 8 itself in sympy. It is not converted into the decimal equivalent. Okay, so let me just update this in the Google document. Update done. I think with this I will stop today because tomorrow we will continue with solving equations and the other stuff that we have uh, as per the schedule, which is as per the schedule we are supposed to solve equations and do something extra with sympy. I will be continuing with discussing more and more operations problems related to sympy. And if there is any clarification questions related to whatever we have discussed so far, you may please ask now. I can try to clarify. Thank you very much for your patient listen. And one more thing is that tomorrow I think the session is scheduled to start at 10 o'clock. Is that right, sir?
That is okay, I think.
Sorry?
Okay, we can conduct it at 10 o'clock.
Yeah, because Sunday and Saturday I think it's better to start at 10 o'clock, and 10 to 12 can we just keep it for Saturday and Sunday alone, and other days we can keep it at 6 itself.
Okay, okay. So we can wind up today's program function, today's session, and tomorrow we will meet at 10 a.m. Thank you all. Thank you, Professor Vishnu, and thank you all participants.
Okay, let me post this in the streaming also. Okay, thank you everyone. If there is any clarification required, even that I can clarify it even tomorrow. Tomorrow anyway we are continuing with sympy itself. So all the programs are posted to the Google documents. You can try with some of these. You can copy and paste, and you can try. Okay. Thank you very much.